Hello everyone. In our last lesson, we used external interruptions to add an alarm setting feature to the electronic clock. In most cases, when the alarm clock reaches the set time, it provides an audible alert. In this lesson, we will learn about the generation of tones and the design concept through three main components: hardware circuit design, program design, and simulation operation. Additionally, we will implement the final feature of the electronic clock, the alarm function, through simulation and debugging. Let's first look at the simulation circuit diagram. The hardware circuit is built upon task 6 with the addition of a speaker connected at P3.7. By outputting square waves of different frequencies through port P3.7, we can generate various musical tones. Let's analyze the method of generating audio pulses. Audio signals are square waves of different frequencies, and each note has its own inherent frequency. For example, the frequency of the note law is an audio pulse of 880 Hz. If we use the microcontroller's output signal to generate this frequency pulse, it can be achieved by having timer T1 operate in mode 1. To generate an 880 Hz audio pulse, the period of the audio signal Tm equals 1/880th of a second. We take half of this period and set the timer to toggle the output port's polarity after counting for half the period. The initial value of the timer can be calculated using a formula, resulting in 64968. Alternatively, the initial value of the timer can be directly determined by consulting a table. For instance, assuming a crystal oscillator frequency of 12 MHz, their relationship is shown in the table below. Let's illustrate with a simple program how to loop through the pitches from duo to so. First, we write the frequency values of duo to so in hexadecimal and store the high 8 bits in an array called voice_high and the low 8 bits in an array called voice_low. The variable m is used to keep track of which pitch needs to be played. The variable k is for use in the delay function. The variable spk represents the level of P3.7. In the main function, we set up T1's timing mode with the initial value of duo's frequency and allow T1 interrupts. Then, we enter an infinite loop that executes the following statement group each time. When m is equal to 0, we turn on T1 to play the duo pitch. Pause briefly, then when m is equal to 1, play the re-pitch, and so on. This is the interrupt service routine for T1. Each time it enters the interrupt, it first toggles the level of P3.7 once, allowing it to output a regular square wave at a certain frequency and produce sound through the speaker. The initial values of TH1 and TL1 are determined based on the current value of m, looking up the corresponding frequency values in the two arrays. This is the delay function, which can adjust the length of time each pitch is played for, whether slow, medium, or fast. Do you find pronunciation not difficult and eager to try? What we need to consider next is how to incorporate this program into Task 6 program to implement the alarm clock sound. Let's look at several key points in the design. 1. Add the two arrays from the pronunciation program below the dis_buffer array. 2. Define the three variables used: m, k, and spk. 3. Add a bit variable called music. When music equals 1, the speaker emits a tone, and when music equals 0, the musical sound stops. For the specific main function, you can refer to this section of the program. 4. Remember to set up T1 interrupts in the interrupt initialization function. 5. It's important to note that the alarm clock should not sound indefinitely like the simple program above. That would be impractical. We need to set a current alarm time, like ringing for 10 seconds. From duo to so for 10 seconds, this can be achieved with this statement. The timer T1 interrupt and delay function remain unchanged and can be added to the end of the program. Let's take a look at the simulation results together. First, debug the program in QELU Vision 5 and load the hex file into the microcontroller. Once the simulation starts, you can see that the electronic clock's time-changing function works normally. I have set the alarm to go off at 6:30 a.m. When the clock reaches 6:30 a.m., the alarm will sound, and then stop. Attentive students might notice that we programmed the alarm to ring for 10 seconds, but it actually rang for 12 seconds. What could the extra 2 seconds be? Have you guessed it? Yes, this is one cycle of playing the pitches from duo to so, which takes about 2 seconds. In this lesson, we have learned how to use the T1 interrupt of a microcontroller to output different audio pulses and implement the alarm function. We covered 7 tasks, from simple to complex, thoroughly learning about digital electronic clocks. If you have also successfully completed this digital electronic clock, congratulations! You now have the ability to control a microcontroller, making even more complex tasks seem less daunting. To conclude, here are a few exercises to test your understanding. That's it for this lesson. Goodbye, everyone.